All right, let's jump straight into this explainer with a quote that completely flipped my perspective. It's from a 2025 paper by Richard J. Reyes, and it fundamentally challenges how we think about computer science. You see, for decades, we've basically treated computation as if it happens in Hilbert's universe, this perfect abstract realm of pure logic where flipping a bit or changing a state costs absolutely nothing. But this paper makes a really bold claim. In our actual physical universe, computation is never free. Every single logical step has a very real physical price tag.
And you know what's really wild about this idea is how it attacks the legendary P versus NP problem. If you follow complexity theory at all, you know brilliant people have thrown every flavor of pure mathematics at this puzzle for over 50 years. But what if we've been stuck because we've been ignoring the physical laws of thermodynamics and geometry? What if the barrier to solving complex problems isn't just about finding a clever enough algorithm, but hitting a literal physical wall?
Today, we are unpacking this incredibly dense, highly theoretical paper called P versus NP in Curvature-Bounded Wave Computation. In it, Reyes proposes something called wave confinement theory. Essentially, it models computation not as an endless string of ones and zeros on some hypothetical tape, but as the physical evolution of confined oscillating waves.
Here's our quick roadmap for today. We'll start with the ultimate math mystery, explore exactly why logic is never actually free, look at how computing with confined waves works, unpack this crazy concept called the dimensional lock barrier, and then finally bridge all this physics back to classical math.
Let's kick things off with part 1, the ultimate math mystery.
You all probably know the deal with P versus NP, but let's reframe it quickly. Traditionally, we assume finding a solution is just fundamentally harder than checking one. It's like a massive Sudoku puzzle, right? Solving it from scratch takes a ton of time and effort. That's the P part, the polynomial time construction. But if I hand you a totally filled out Sudoku grid, you can verify if it's correct almost instantly. That's the NP part. Proving mathematically whether these two classes are actually different or somehow secretly the same thing has completely stumped the experts. And it's absolutely crucial because literally our entire digital world, from bank encryption to secure messaging, relies on this assumption.
Which brings us to the paper's massive paradigm shift part 2, why logic is never free.
Classical Turing machines basically live in a fantasy world. They assume state changes cost nothing, memory is perfectly stable and infinite, and logic is entirely free. But this new wave confinement theory, or WCT model, drags computation kicking and screaming into physical reality. It demands an energetic and spatial price for every single logical step. You can't just magically teleport to an answer. You have to physically build the path to get there.
Think about it this way. A jump from not knowing to knowing requires a physical journey. We actually already know this from Landauer's principle in physics. Just erasing a single bit of information dissipates a tiny amount of heat energy. Well, the WCT model takes that idea and runs with it. It argues that information is an actual structure in a physical field. So to evolve a system to solve a problem, you are literally bending space, accumulating curvature, and generating entropy. The path to your solution has a strict geometric budget.
So, how do we actually model those costs? That's part 3, computing with confined waves. Okay, scratch the idea of flipping discrete bits on a one-dimensional tape. Instead, I want you to picture computation as ripples and waves interacting on a grid. In this theory, a computational problem is represented by a target, coherent wave state. An algorithm isn't a string of code, it's the physical evolution of an initial, simple wave field rippling outward. It's constrained by the curvature of the space it lives in, eventually trying to lock into a stable geometric pattern.
Let's ground this with an example. Take a classical logic problem, like a 3-sat Boolean formula, and physically encode it into spatial wave interference. Instead of just true or false, you're working with constructive or destructive wave phases. A logical clause becomes an actual spatial region where waves interact with each other. Solving the problem just means finding a state where all these waves constructively interfere and stabilize. You are quite literally achieving physical resonance. Boom, problem solved.
Now, because we are operating in this physical wave universe, the paper defines new complexity classes to mirror our classic P and NP. Think of PWCC as the wave states you can naturally evolve into quickly without busting your physical energy bank. On the flip side, you have NPWCC. These are incredibly complex wave states that are super easy to verify once they are locked in, but practically impossible to grow from scratch.
And this leads us to the absolute core of the paper. Part 4, the dimensional lock barrier. This is the physical obstacle that makes solving complex problems so punishingly hard. The dimensional lock basically says you can't just magically jump to an NP solution. To get from a blank grid to a highly complex, non-uniform target state, you hit a massive geometric obstruction. To physically form that solution, the wave would have to bend and curve in ways that require more physical dimensions than the grid actually allows. It is structurally impossible to do it quickly. The author actually ran wave evolution simulations to test this, trying to reach a known target state, and the empirical evidence is stark. As the grid size, which represents real-world problem complexity, grows larger, the bounded wave completely fails to reach the target coherent state. The overlap between where the wave ends up and where it needs to be just plummets towards zero. The wave simply cannot navigate the geometry required.
Let's put some hard numbers to that simulation. They ran the exact same 5,000 algorithmic steps for different sizes. At a grid size of 32, we see a tiny final overlap of about 0.0776. Double that grid size to 64, the overlap drops all the way down to 0.0120. Push it to 96, and it literally goes negative. It's at negative 0.0060. The physical model simply cannot traverse the necessary curvature path to solve larger instances. The dimensional lock stops it dead in its tracks.
So, the grand conclusion within this physical wave framework is that PWCC absolutely does not equal NPWCC. Thanks to these geometric locks, there are highly structured wave configurations that you can verify instantly, but that are physically impossible to grow from scratch within a reasonable energy budget. Construction and verification are fundamentally physically asymmetric.
But wait, how does a physical physics problem link back to pure computer science? Let's hit our final section. Part 5, Bridging Physics and Math. The trick here is bridging these physical wave constraints back to traditional, discrete Turing machines. The author proposes that you can treat these fluid wave configurations as finite precision binaries and simulate the updates using standard log-depth computer circuits. The major hypothesis here is that traditional computers and these theoretical wave machines can simulate each other efficiently with only a small polynomial overhead.
And here is the absolute payload. If this bridge holds up, if a classical computer simulating this physical wavy universe is mathematically equivalent to the abstract Turing model, then the physical dimensional lock we've been talking about would definitively prove the classical conjecture that P does not equal NP. The physical geometry of the universe itself would enforce the limits of our abstract algorithms.
It totally melts your brain a little bit, right? It forces us to realize that computation isn't just floating out there in an abstract void. It happens right here, bounded by space and time. So I'll leave you with this lingering thought to wrap up our explainer. If pure mathematics is ultimately constrained by the physical laws of our universe, does a cost-free Hilbert's universe even exist at all? Or is it possible that our deepest, most fundamental mathematical truths are actually just prisoners of our physical reality? It's a lot to chew on. Thanks so much for exploring this with me today.